Good morning all. The next section is magnetic vector potential. Before that, let us compare magnetostatics and electrostatics. In both magnetostatics and electrostatics, we have studied the divergence and curl. What is the divergence and curl of electrostatic field? For electrostatic field, we have del dot E, that is divergence of E is equal to rho by epsilon 0, that is called Gauss's law, and also the curl of E, del cross E is equal to 0. No name. These equations are called Maxwell's equations for electrostatics. Maxwell's equation for electrostatics. In the same way, we can write the divergence and curl of magnetostatic field. Divergence and curl of magnetostatic field. First, the divergence of the magnetic field del dot B, which is equal to 0. Then del cross B is equal to mu 0 j. Del dot B is equal to 0, no name. But del cross B is equal to mu 0 j is called Ampere's law. These equations are called Maxwell's equations for magnetostatics. Maxwell's equations for magnetostatics. This is the comparison of magnetostatics and electrostatics. Now let us discuss magnetic vector potential, an important topic in magnetostatics. We have studied the scalar potential V in electrostatics. In electrostatics, we have del cross E is equal to 0. When del cross E is equal to 0, we have E is equal to minus del V. That is, del cross E is equal to 0 permitted us to introduce a scalar potential V in electrostatics. Del cross E equal to 0 invites to the introduction of a scalar potential V in electrostatics. Mathematically, it is true because the curl of a gradient is 0. So we can write E is equal to the gradient of a scalar potential. In magnetostatics, we have a similar equation, that is del dot B is equal to 0. Del dot B is equal to 0 invites the introduction of a vector potential A in magnetostatics, that is B is equal to del cross A. When del dot B equal to 0, we can write B is equal to del cross A. Del dot B is equal to 0 invites the introduction of a vector potential A in magnetostatics. Mathematically, this is true because the divergence of a curl is 0. So when del dot B is equal to 0 means we can write B is equal to the curl of a vector function. We have the differential form of Ampere's law, that is del cross B is equal to mu 0 j. We have seen B can be represented as del cross A, where A is the vector potential. Now del cross B is equal to mu 0 j becomes del cross A, which is equal to mu 0 j. Now we can represent del cross A as del of del dot A minus del square A. Del cross A, which is equal to del of del dot A minus del square A. Hence, del cross A equal to mu 0 J becomes del of del dot A minus del square A, which is equal to mu 0 J. Now suppose del dot A is equal to 0. Then del square A can be represented as minus mu 0 J. We can simplify the expression we can simplify the expression to del square A is equal to mu 0 minus mu 0 J if del dot A is equal to 0. Can you make del dot A is 0? Yes, it is possible. This is because we have B is equal to del cross A, where A is the vector potential. Suppose we are adding any function to the vector potential. Suppose we are adding any function to the vector potential A. The function is selected in such a way that whose curl is 0. Then what happens? Suppose we add a function to A. The function is selected in such a way that whose curl is 0. Then we can say that the magnetic field remains the same because B is equal to del cross A, and suppose we are adding a function whose curl is 0, then magnetic field will not change. Now we can use this property to make del dot A equal to 0. When del dot A is equal to 0, the equation simplifies to del square A is equal to minus mu 0 J. Thus, by selecting a suitable function, we can eliminate the divergence of A, or we can make del dot A is equal to 0 and reduce the equation to del square A is equal to minus mu 0 J. But the function is selected in such a way that whose curl is 0. Why? Because the magnetic field should not be affected by adding some function to the original vector potential. The function is selected in such a way that the curl of the function is 0, so the magnetic field B is not affected. Now let it be del lambda. We are adding del lambda to the original vector potential. Why we are selected del lambda? Because curl of del lambda equal to 0. The curl of a gradient is 0. So you can add the gradient of some function to your original vector potential so that the magnetic field is not affected. Now you assume that A0 bar vector A0 be the original vector potential. Let the new vector potential be A, that is A0 plus del lambda. Here remember that by adding del lambda the magnetic field is not affected. There is no change in the magnetic field produced. So we have the freedom to add del lambda to your original vector potential. Now let us evaluate what is del dot A. Del dot A becomes del dot A0 plus delta lambda, that is del dot A0 plus del square lambda, where del square is a Laplacian. Thus del dot A becomes del dot A0 plus del square lambda. Now how to make del dot A is 0? Del dot A is 0 if and only if del dot A0, that is equal to minus del square lambda. So if del square lambda is equal to minus del dot A0, you have del dot A equal to 0. When del dot A equal to 0, your equation reduces to del square A is equal to minus mu 0 j. So we have to find out a lambda for which del square lambda is equal to minus del dot A0. And for that particular lambda, you have del dot A is equal to 0. Now your equation reduces to del square A, that is equal to minus mu 0 j. Now to find lambda, we need to solve the equation del square lambda equal to minus del dot A0. This del square lambda is equal to minus del dot A0 is of the form del square V is equal to minus rho by epsilon 0, a well-known equation that we have studied in electrostatics. This equation is called Poisson's equation. Del square V is equal to minus rho by epsilon 0 is called Poisson's equation. And the solution of the Poisson's equation that we have already studied, that gives the value of the scalar potential V. So this is equal to 1 by 4 pi epsilon 0 integral rho d tau by r. Now our equation del square lambda equal to minus del dot A0 is of the form of the Poisson's equation in electrostatics. So this equation can be solved in the same way. Hence del square lambda equal to minus del dot A0 can be solved. The solution is lambda is equal to 1 by 4 pi integral del dot A0 by r into d tau. Now while selecting the Poisson's equation, we have assumed that rho tends to 0 at infinity. Now in the same way, in the equation for lambda, lambda is equal to 1 by 4 pi integral del dot A0 d tau by r is valid when del dot A0 tends to 0 at infinity. Thus by choosing a particular lambda, we can make del dot A equal to 0, or we can make the vector potential, or we can make the freedom to eliminate the divergence of A, or we can make del dot A is equal to 0. Now let us recollect our equations. Del cross B is equal to mu 0 j, that is the Ampere's law. When B is equal to del cross A, we have del cross A is equal to mu 0 j. Now del cross A can be written as del of del dot A minus del square A, that is equal to mu 0 j. Now we have selected a value of lambda, that is 1 by 4 pi integral del dot A0 d tau by r, for which del dot A is equal to 0. Hence our equation reduces to del square A is equal to minus mu 0 j. Now to evaluate the vector potential, we have to solve the equation del square A is equal to minus mu 0 j. If we look the equation, this equation is again identical to the Poisson's equation that we have seen in electrostatics. So this equation can be solved in the same way that we have solved the Poisson's equation. Then on solving del square A is equal to minus mu 0 j, the solution is A of r is equal to mu 0 by 4 pi integral j of r prime d tau prime by r. This is for volume current. Now we can define the vector potential for line current and surface current also. Now for line current, A is given by mu 0 by 4 pi integral I dl prime by r And for surface current, this is equal to mu 0 by 4 pi integral k dA prime by r. Mu 0 by 4 pi integral k dA prime by r. These are the equations of vector potential in magnetostatics.